Hello and welcome back to a new video here on the Ludwig Fusel channel. Last time we have talked about the holy big three. The holy big three were basically three functions that we implemented on every class, or that we're going to implement on every class, or you're going to implement on every class you're going to write in your life. And they were the destructor, the copy constructor, and the copy assignment operator. So the idea is that you have fully controlled memory management by providing these three operators so that you don't have memory leaks, that you don't spend computation times, that everything is deterministic, and everything gets copied instead of recomputed, and memory management doesn't kill you. Right? Correct releasing of your data, correct assigning of your data by first releasing it and then copying it, correct copying by copying trivial and more complex data by copying arrays instead of recomputing them or just copying around pointers. And the whole idea here is that you can create a unique, deep copy of your objects. Now, big three are good, but 5 is always better than 3. So we're gonna today talk about the big 5. And to understand the big 5, we first need to understand the problem. First of all, let me get rid of the problem that we don't need, right? We have understood reference, we have understood the idea of copying, we have understood everything here. So print PC is really not something that we're gonna need anymore, and we can go again back to our PC print here. All right, so what I want to talk about now is I want to talk about, doing a bit of more with your objects. So you can see that we have created the function precacher here as a class in here. And what I now want to create is I want to create a new class that manages function precachers. So let's call them precacher or precacher container. So this is going to be a container out of function precachers. We're going to implement this one very simple. I always tend to start like that and implement this as I go. And what I now want to do is I want to now create this one in a correct way. So how I'm going to implement this one, I want to actually store function precachers. So let's create an array of them and let's call them precachers. So precachers, let's say we want to store 8 of them in maximum, so we're going to call them precachers 8. All right, so one thing that I always tend to do on classes, I always tend to preprint m underscore. M underscore is always meant for member underscore or my underscore or whatever you want to do this. It's generally mean for members, but I tend to call, I always like to call them my precachers because it always is good to say if you're reading code, okay, this is my precachers, even though members is actually meant. And what I always tend to do is then also write it like that, m precachers. All right, so we're going to have an array of precachers, and I'm also going to store myself an int, which is the, let's just call this usage, and by default, the usage is going to be 0. All right, so what I want to do is I want to assign the function precachers in here. Now, I told you that we always want to fulfill the big 3, so there are 3 functions that we need to implement. That one, the destructor, which I'm going to assign to the default one because default, not delete. I want to assign this to the default destructor because I don't do anything special in here. I don't have any members that need special treatment. These are function precachers. They are already managing themselves. We have already written the destructor in here. So there's really no point in writing custom destructors here. So I can just say default to tell the compiler that we want to use the default constructor. This doesn't need to be done explicitly. I have done this now explicitly. Normally, if you just leave it away, it's done implicitly, so it wouldn't be required. I can comment this out and it would still work the same. However, since we are trying to always fulfill the big 3, I always tend to write them in here. Same goes for my copy constructor, which I can also take a default version for, because again, the default version is going to try its best at copying, and since it's already implemented in here at each object, it's already going to do this automatically, right? The compiler's not stupid. If it finds a member that already implements a copy, then it's also going to invoke that copy, right? The default version is always try to invoke the default one, and if it knows how to do this, because it has been already specified in a different class, it's of course automatically going to do it. So yeah, that's how it goes. Another one missing for the big 3 is our move assign. Same goes for that one as well. Missed that one. Same for that one. We also take the default implementation. So just going to assign this here to default so that everything is good here. So everything is on default of the big 3. We don't need to change anything, but I like to explicitly write them down because I want to follow them. If I take a look at the class, I want to see a custom implementation, a default, or a delete. I want to always see these. If I do something like that, I want to see these ones. It's important. I always want to see them. No way around them. What I also personally tend to do is, if I don't have a constructor, I always also try to explicitly specify the default constructor. This is not related to the big three, this is just related to my good practice. And in my good practice, if I don't supply an implementation, you're always going to find that one in every class that I write. If it's a trivial class where everything is implemented by default, you're still going to have these 3 lines here and that 1 line down there. I always do this even if I have no implementation, just for good practice. And I would recommend you doing this as well, because if somebody takes a look at the class, they can directly see that you have thought about it. That implies you have thought about somebody assigning these. You have thought about somebody try this. And if somebody takes a look at this and sees that code in here, they know, all right, okay, I can do it. It's a default implementation. Always have it like that. That's just a suggestion from me. All right, so now let's actually add some code to that one. I want to have a void print. The void print should print all that are in here. So what I'm going to do here is I'm going to do a for loop, e equals 0, and I'm only going to print how many I'm going to use. So smaller than usage, m usage, or my usage here. And then I open the brackets, and instead of here, I'm going to see out something like, let's maybe do a see out here as well. Let's say see out container at then the sys pointer so that I have the address. Okay, something like that, and then I'm gonna say function precacher hashtag the index that we are using, which is I+1. I always like to then do, you can do this like that. This works, but I tend to do math computations in here in brackets so that you can see that they are explicitly computed here. Just some style that I tend to append here. I try to kind of like teach how I would program this. So you can see like now I'm first echoing out the container, then I'm echoing out the number of the precacher, and then what I want to do is that the m precachers at the position I want to call the print function. As simple as that, just to print them all out. Right, now the only thing left to do is to actually write a function that appends a function precacher. Now let's call this one append as well. So I want to append one, and what do I want to append? Well, I want to append a const function precacher reference PC. So I want to append that one to there, and what I'm going to do here, if usage is smaller than 8, so currently it's 0, which means no usage. If it's smaller than 8, I want to increment the usage, so usage ++ to create a new one, and inside of my precachers at the position usage, now this is important that this one is actually before that, I'm going to assign my PC. Like that. You can see this is a const reference, and as soon as I'm assigning that, it's going to create a copy out of that. You could already do a copy here, but if you're doing a copy here and assign it there, you're going to have 3 versions. The original one for that function and the one stored. In this case, I have the original one and the one stored. So this is where I have a const reference here. It's a const reference. I can't change PC, but I can copy PC over to there. This is why I'm doing it like that. What you can also do is musage ++. This is the post increment. I think we talked about that in C, but I'm going to explain it anyways. So musage ++ is going to take the old value, so it's going to take the values on the left. It's on the left, so it takes the old value and then it increments it by 1. If I would do ++, musage is going to increment it and then takes a new value, but I'm going to use musage ++ to get the old value, so 0 in this case, and then I'm going to increment this. So this is going to make sure that everything is stored. And if you do this like that, it all looks good. And what we can do now is we can easily now store function precachers inside my container. So what I could do here is I could put all these function precachers in there. So I can say, all right, I do a PC here, and then I want to do something like, first let me create actually the container. This is of course required. So let's take the container and call it CNT for container, and then I'm going to say CNT append my PC. So I can append the PC, then I can call, for example, setup again, then maybe let's say x times 2 and count at f, then let's say CNT append again, so I'm gonna append that one, and then I can say like setup again, and then I'm gonna say x count times 2 and f again, and then I can say cnt append pc, and finally I can see cnt print, and the idea is that we now get a output from all of these containers. So let's try this out. 5 and 5, and now you can see that we have a container at that address. We get one output with 55, 155, and all of that, and then we get the same values again. Okay, I get the same values again because I haven't cleared them. The idea would be that okay, of course I need to call compute again. Setup and compute always needs to be done like that, and I think I might even need to call clear before that, or I need to change my pre-cachers. I think I actually need to change the pre-cachers because, yeah, they are not going to allow setup if data is already persistent. That's something that I want to change. If I call setup, I actually want to make sure that I set them, and before that I want to call release, so that if we call setup again, all data is released, and then we're going to set up again. That's the idea here. Oh no. So if I add that one in here and I would run this now again, I would now suspect that it works, and yeah, surely it does. 55, it has all the number ranges, here's the double of the x, here's the double of the range. We could also add another one, but I think that the code is already quite complicated. So as you can see, it is all working very, very nicely, and all comes together like a charm. Now, what I want to do here is I want to simplify my code. You can see that this one is looking quite ugly to append these. What I want to do is I want to be able to do this a bit more cleaner. Now, as I told you, you can create this. We have experienced this by accident, that you can create a function pre-cacher like that. So what I could do is I could do something like that, and I would have created an object by accident without a name. However, if I would put a dot in here, you can see that I actually have the compute function available. However, as you can see, this compute function is returning a void. So if I would try to append something like that, so if I would try to call like append of that one, it wouldn't work. Right? It wouldn't work because we can't append them in here. So what I really want to do is I want to allow that something like that can be appended. Or do I want to allow this? Maybe, maybe not, maybe yes, but I want to do it. I want to be able to allow that this one works. How can I do this? Well, in general, I just need to return a reference again. I need to return a reference if I call compute. So I can like say function pre-cacher reference is going to be the return value of the compute function. And again, return the reference to get from the pointer to the reference, if you could spell this right. And if I would do this like that, so I get a reference, then you can see that this one would be a total valid syntax. So what I could do is I could do this like that. This would then bring us up and make the code way simpler. Do a times 2 to here, times 2 here, and multiply that one in there as well, so that we have a few versions of them, and append them all to my container. So you can see that this doing my code like that already makes the code way more readable. This one we don't need it, so we create a container, and then we're gonna append to that container, do the computations, and put them in there. And if I do this like that, boom, you can see we get the same output. Again, no, not exactly the same, because this one is getting a few different values, and we now have like 4 outputs of them, but the general idea is still the same that's going on here. Now, do we have a problem with that code? We have a problem with that code. The compiler might be already smart enough and already have stolen my problem, but I hope it has not, because then the total video and everything, the whole build-up would be pointless. What I'm doing here, and I need to quickly come up with another example, but let's quickly instrumentalize our code again and show you what's going on here. So in general, what I instrumentalize, I want to quickly instrumentalize my release and my compute. Let's do a quick cout allocate to quickly say that we are allocating. I don't care about what the object is. I'm just going to say quickly allocate. Or maybe I don't even want to say allocate. I maybe want to just quickly tell which function was called. So let's do something here on compute. I want to do something similar on release. So let's get release in here. So we have compute and release. I think this might be already enough. No, I want to have this as on copy as well. Copy is at some point calling the copy constructor. So I want to maybe do something like copy here so that we have a bit of an insight what's going on here. Let's now press F5 and see what it is doing. And I hope that the compiler really doesn't kill me. But it actually looks good. Okay, so what you can actually see is that we do quite some computations. Okay, I call now release every time. This is not good. I should have instrumentalized this better. Okay, let's actually instrumentalize when the operations happen. Let's actually put the copy in here. To put this down there. To have the copy here. And I want to also quickly put the compute only when I have done it. If I'm actually doing this, I don't care about indents here. It's just to quickly visualize this. And then I want to quickly also comment out my print here so that we don't get spammed here. All right, so let's do this like that and show you what's going on. Okay, so now again, entering the values and showing you what's going on. All right, as you can see, what's happening is that we are computing an object. So an object was created that computed the data. The object was copied, so we allocated a new array. We have copied over to the new array. Then the old one got released. So we computed one, we released one. We created a copy for that. Maybe I should have added the addresses in here as well. Alright, so I've quickly added again the addresses so that you can really see what's going on, that this is a bit more self-explaining. So the idea here is we are computing the value of tier 1 to 100. We are copying from to 100 to the newly allocated 2830. We are releasing to 100. We are computing 22E0. We are copying from 22E0 to 28E0. We are releasing 22E0. And then again, the same thing. So really what you can see a pattern. We are allocating data, we are copying data, and we are releasing it. So generally what's happening is we are allocating an array to then directly release it after we have allocated a new one and copied over to that. And as you can see, this is kind of wasteful, right? Because we are allocating data and we are directly discarding it. So in general, what's going on here is if I go down into my code again, into my main, what's happening is that this call here is allocating the data. Then the append one is copying the data. And then, since the function returned and this object is only living like inside this append call, it's destroying the data. It's destructing the object, which is releasing the data. So really what's going on here is that we have wasted two arrays. So we use 2 times the memory and we use the computation time to copy data over. So really what we have done is we have found a situation where it would be better to do a plain copy of our object. A plain copy without any intelligence. A plain mem copy here, in this case, would be totally fine. But the compiler doesn't do this because, well, we are appending it as a copy. And this is where we are getting to the big 5. So the big 3 was destructing, copying. Assigning and copying in general. Assign construct and assign copy. Or copy assign, whatever you want to call it. So in general, like these 3 functions that we implemented. Destructor, copy assignment, and copy constructing. Now the big 3 is an extension to the big 3. Now the big 5 is an extension to the big 3. So we already know 3/5 of that. So we already know the major thing of the big 5, even though we don't know what the big 5 is at all. So the idea of the big 5 is to add 2 more functions to your object. And the functions are the so-called move constructor and the move assignment. Now, basically what move means take ownership. So the idea of a move constructor or a move assignment is that you are stealing the data of an object. So it is kind of like the plain copy that we had previously without any implementations, but explicitly stated. Move assignment, move constructing. Getting another object and stealing the pointers from it in our idea, or stealing all the resources. So the idea is, if you are move constructing an object, the object from where you are constructing is discarded. So in this case, you can see this object is discarded anyways, because after that function call, this object is going to be invalid. It's going to be destroyed. And so it would be totally fine to take its internal data and steal it from it. so that we can use it. And that's the whole idea of the move assignment. Now, move is a very special construct of the C++ language, but I'm going to show this to you how this works. So in general, the move is operating the same way than a copy would work. So the idea is the same. The idea is you're having a reference to a different object. However, now, since you want to actually steal the data from the other object, this object is no longer be allowed to be const. Now you are stealing the data, so you can actually tinker around on the object however you like. Because this object is going to be invalid, and using this object afterwards is defined as undefined behavior. So this is why the move constructor doesn't need a const. However, if you would take a look at this, this looks like a normal reference. How can we distinguish this reference from moving the data? So copy from move. Like, this is a reference, so we would expect that we just access it, but we don't really think that we are invalidating this object. Well, the move is designated by having 2 ampersands. Now, this really doesn't make sense. This looks like a double reference or something like that. However, double reference is not a thing there. References are always just gonna be to one type. You always have a type and reference. A double reference is not like with a pointer that you have like a double pointer. It is meant for being a move semantic. It's called move semantic. Now, as you can see, if I write this, the compiler isn't really happy with my code. You can see it's not red. The underlines are not red, and not red is good because red is error, and green is just, hey, suggestion. Do you mean to do something? And if I hover over that, we're gonna get a warning here, which tells us the kind of function should not throw. Declare it non-except. Now, we haven't talked about exceptions yet, so this doesn't make any sense to you. It's asking us to add non-except, declare it non-except. And how to declare it? It is similar to const. If we had const here, which doesn't make sense, we always wrote it after the function, somewhere down there when we printed, right? When we printed, here we had const, and so we should also write the no except there. So no except. This is something that we're going to write here, and you're going to see if I give my IDE a few seconds time, it should disappear. Disappear, come on. They're gonna disappear in a few seconds, probably. But adding this no except basically declares this function as not being allowed to throw exceptions. We haven't talked about exceptions, but the idea is that move is not throwing exceptions because it's basically a plain copy of data. And this is why we need to add this here. We're gonna explain this in the whole depth later on. Alright, so let's continue on writing the code now. Now, if we want to write code here, we should have like some trivial copying. And trivial copying would mean that we want to copy all of these four values. And actually, this is totally right. We just want to plainly copy all these values over in the code. So x equals other x, count equals other count, function equals other function. And now, even this seems now from everything that you have learned totally wrong. Values equals other values. A plain copy of the data. Nothing fancy with memcopy, just a plain copying. And now you can see that it has removed the underlines. Now, of course, it's called the big 5, not the big 4. So what we also need is the move assign. The move assign, very similar to that one. So we can copy this over. Only difference, this is not const. This needs a double ampersand, and this needs a no except. Same idea than previously, and also calling the constructor. Now, this is really important. If I hover over that, you can actually see that it is still calling the non-move constructor here. How can we force it to use the move constructor? We need to tell it to move it. How can we tell it to move it? Well, this is different. You need to call std move. Std move looks like a function, and it kinda is. If we would take a look at this, you can see that it does a some remove reference, move, remove reference, static, cast, reference, arc. It is doing something interesting there. We really don't understand what's going on here, and we don't need to understand what is going on. Basically, this is forwarding argument as movable. This is in general just telling the compiler that it should be moved. Normally, it is not automatically calling move. If I now hover over that, you can see that it now calls the proper move constructor. It is just important that you do it like that. You could also implement this here again with calling the release function and then moving over as well. But in general, the idea here is that you want to write it like that. And now you think that everything is good, right? Everything is good. You have implemented everything correctly. You have added the move, and now it should be used automatically like everything else in our code, and we should press a 5 and it should magically work, right? Let's see. And wrong, it doesn't work. Why does it not work? Well, because move is something that we need to do explicitly. And as you can see, here somewhere, where is it? I have to call move, std move, to move the object. This is just inside std namespace, that's why it's std move. And since we have called this one here explicitly as well, we need to explicitly call this above in our, or down here in our function cacher, or in our pre-cacher container as well. So currently we have just a normal append function, and now we also want to write an append function that is being able to move an object. So in general, the idea is that we have a function pre-cacher reference, so movable PC. And if we do it like that, we can now correctly implement the move operations by calling std move PC. I mean, that it might already called this one correctly without move. It might have, it might not have. Let's see. No, it has called the copy, so we need to manually call move. Move in general, just always use it. There are certain times where the compiler might automatically use your move, but really don't assert a compiler of doing it correctly. Always, if you're working with move semantics, always use std move to move the object over. So moving is not copying, it's moving the ownership. And now by implementing these functions, did we solve the issue? Let's try it out. Let's enter 5 and 5. And we can see that we still haven't solved it. And we haven't solved it because, again, it by default always copies. If we want to move it, we want to explicitly std move it. And now a little Visual Studio trick. Hold the Alt button, left click, left drag, and you're gonna write everywhere. This is just really useful. Only down here it doesn't work with escape, you can always get out of that. And what I'm gonna add is the std move around everything here, and you can see if I add std move here and cover over the append function, it is now using the correcty appendy one. And if I now would press a 5, you should see a issue. Now, what is the issue? Well. Actually, what happens is, again, that we try to delete an object twice. You can see that, for example, this E590 was the last one that was created, and it was released twice. Why was it deleted twice? Well, because move is a lie. Move in C++ is a lie. Move is not a thing at all. Move is just a language construct. Move is a lie, even though it is on a big 5, it is still a lie. What is the problem with that? Well, this object here is, if you consider the code here, like that, and the output here is already the output, you can still see compute release. It is still destroying that object when it goes out of scope. So what it is still doing here, as soon as this append is done, it is still destroying the original object. Why is it doing that? Well, because, as I told you, move is a lie. We need to actually invalidate the object if we are calling std move. That one is just copying the values over. You also need to invalidate the other object. So the only thing left to do here is set that one to null pointer. If you are invalidating the pointer of the original object that you are getting in here, and this is also why this is not allowed to be const, because you need to modify it in here. If you are setting that to null pointer down in here, then the destructor will fail because it cannot free it. And if I do it like that, we should get... Why did you directly stop here? Or didn't give me output? I don't know. Let's restart here. Okay, there we go. 5 and 5. Now we get what we are talking about. Now we are not getting any errors. We are getting 4 times compute and 4 times release without any copying or like compute, copy, release, compute, copy, release, compute, copy, release, 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 release. No, we are just getting plain compute, compute, compute. We are 4 times generating the array, and at the end we are 4 times releasing it. So C++ is all about optimizing your stuff, and the big 5 is the right way to do it. Your move, assign, move, construct, and all that stuff. So really, it is still a complicated concept, but not that complicated at all. The only thing why you can beat me now is that I haven't written const here, because I already violated my const correctness. This is completely const correct, because you should still be able to append with already existing data so that it can be copied, but that one is something that you should also be concerned about, so that somebody can also move the ownership of his function precacher in here. So really what we have done today is we have written or made our code way better. The only thing left to do is really to get rid of all that trashy instrumentalization code around here. Oh, something like that, we don't need it. We didn't need it. So there we go. Now it's looking nice. And now if we run it, you can see std move is all called. And if we run it, 5 and 5, we get the correct output and we have minimal memory overhead. Really, we are doing 4 memory allocations and 4 memory freeings. And this is exactly what the idea of how we are calling it implies. It implies that we have 4 instances that is at some point destroyed. So it applies 4 allocations, it applies 4 frees. And if you're doing it like that, it is completely doing it as you expected. It's not doing any copy behind the scenes. It is not doing anything at all. However, it can always do it. That's the full nice idea behind it. The idea behind everything that we are doing here is the idea that you can always do what you want. You can always do what you want. Everything works. If you do it like that, function precacher pxxxx, like 5555f, something like that. Again, you don't need the ampersand. I told you that on C. ppx, and then you can do your function precacher px equals pxx, and then you want to say that your like function precacher py equals std move from px, and you can really do whatever you want. You can move data around, create them, copy them, do whatever you want to do to them. You just need to tell it if you want to move it, because if you don't want to move it, it's always going to copy it. Again, if we wouldn't have a, and that's how in general the idea of move semantics work. And even though they seem quite complicated, they are really handy and they are really important to understand. And now I'm gonna tell to you, congratulations, you have done whatever you need. No, you have one thing that you have not done. You haven't considered the big 5 here in our precacher container. The precacher container, of course, also shall implement our big 5, even though it is the default implementation. Still, you're gonna see my code like that, because this is telling you that I have thought about that, right? I have thought about that. I have thought about what happens if you move them. Important. So that's it for today. Thank you for watching. See you in the next video. Make sure to like and subscribe, and yeah, have a nice day and have fun with your moves. Bye.